Welcome. In this video, we begin Unit 10, Composite and Inverse Function. Today is day 1 of the unit, where we look at composite functions. This is section 6.1 from the book, and there are 2 objectives, and we will cover them both. First, let's form composite functions. So, by way of example, suppose f of x is x squared, and g of x is 7x plus 1. Then I can put one function inside of the other. Let's put the g of x inside of the f. And so the g, this entire 7x plus 1, that takes the place of the x in f. And so I get the whole thing being squared. So f is the x squared function, but inside of that is 7x plus 1. I can go the other way too. Let's suppose that I want to figure out g of f of x. So f of x goes inside of g. So this whole x squared goes in the place of where the x is. And so I end up with 7x squared plus 1. Here are a couple for you to try. Pause the video, work these things out, and then start the video again to check your work. Let's take a look. So in this first example, f is 1 over x, g of x is x squared plus x cubed. F is the big function, f is the outside, and g is the inside. So the overall form of this looks like 1 over 1 minus something. And what that something is all of g of x, x squared plus x cubed. It is really important to put the parentheses around there because this is a subtraction. For g of f of x, the overall form looks like g, so I have something squared plus something cubed. But what goes inside of g, that's my f of x. That's this whole 1 over 1 minus x. So 1 over 1 minus x goes there, 1 over 1 minus x gets cubed. And then for the last example, let's say f of x is the square root, and g of x is the absolute value of x plus 3. In the first case, where f is the outside function, the overall form looks like the square root of something, and the something that goes in there is g of x, so that's the absolute value of x plus 3, like that. In the second case, if g is the outside function, then overall this looks like the absolute value of something plus 3. Well, what goes into those parentheses looks like the square root of x. Now, I don't really need parentheses there, so let's just call it the square root of x. Notation. So the composition f of g of x is also denoted like this, with a little circle between the f and the g. And we read this, f of g of x. So you'll often just see this, and you have to remember that means that f is the outside function and g is on the inside. For example, if f is x squared plus 1 and g is 3x plus 4, f of g of x, well, it looks like the f on the outside, but what goes in place of x is 3x plus 4, like that. So when you see f of g, please remember, g is on the inside and f is the outside function. Let's evaluate a composite function at some different numbers. Let's say, again, for example, f of x is x cubed, and g of x is x minus 1. Well, f of g is a function just like any other function, so I can evaluate f of g at the number 3, or I can evaluate g of f at the number -1. Let's give this a try. So in the first case, f of g of 3. So the first thing I do is I look at the g function, and you can kind of remember this because g is closest to the 3. So I first figure out g of 3. So g of 3 is 3 minus 1, that's 2, okay. I figured out g of 3, that's 2. Now I take the 2 and plug 2 into f. So f of 2 is 2 cubed, which is 8. So my answer is 8. For the second problem, g of f of -1, let's first figure out f of -1. So this is -1 cubed. Oh, -1 times -1 times -1, that's just -1 again. Now I need to take g, now I'm on the outside function, g of -1, that result. And so I find -1 minus 1, which is negative 2. There we go. The domain of composite functions. Let's say that f of x is 1 over x minus 2 and g of x is the square root of x. What is the domain of the composition, f of g? This isn't difficult, but it takes just a little bit of work and just a little bit of attention to detail. First, notice that the domain of g of x is all x that are greater than or equal to 0. So x can't be negative. G of x is on the inside. That's what's kind of most important. Let me write this out. F of g of x. This is what I'm thinking. So the kinds of x that I plug in, initially, at least they have to be in the domain of g to make this thing work. So I know for a fact that this x must be greater than or equal to 0. But we need to be a little bit careful. Next, notice that the domain of f is all numbers except 2. So the g of x, that whole value, g of x cannot equal 2. So I ask myself, what x makes g of x equal 2? And the answer to that is 4. We can figure this out by actually just solving, say, g of x equals 2, so g of x is the square root of x equals 2, square both sides, x equals 4. So x equals 4. So that 4, that is an offending x value. Even though that x is in the domain of g, that would make g to be the number 2, which isn't in the domain of f. So I have to remove 4 from the possible domain of the composition of functions. So the domain of f of g is all x such that x is greater than or equal to 0 and x is not 4. Here's the rule in general. The domain of f of g is the set of all x in the domain of g of x for which g of x is in the domain of f of x. In other words, it is the domain of g excluding those x for which g of x is not in the domain of f. So maybe you need to pause and read this over a few times, really think about it, and look at this example. It's not difficult, but you need to pay attention to some detail. Let's give this idea another try. Find the domain of f of g, where f of x equals 1 over x plus 2, and g of x equals 4 over x minus 10. So I start with the g of x, in fact, because that's the inside function in f of g. So the domain of g of x, we'll say x is not equal to 10. So basically, I can throw anything I want in there except x equals 10. What about f? The domain of f, it's kind of similar idea. It's all values of x except negative 2. X can't equal negative 2. So I'm kind of thinking that x can be, from the first line, x can be almost anything except for 10. But I need to watch out. Is there some x that's going to make my g value actually equal to negative 2? Let's find where g of x, so find those x that make g of x equal to negative 2. Okay, so I'll set my g of x, which is 4 over x minus 10, equal to negative 2. Multiply both sides by x minus 10. 4 equals negative 2x plus 20. Let's pull the negative 2x over to the left, so I get a positive 2x on the left. And if I subtract 4 from both sides, I get 16, and this gives me x equals 8. So this is a bad point, a bad x value, because if I were to plug in 8 into my g function, that would make negative 2, which can't work for f. So my solution then, what is the domain of f of g? It's the set of all x such that x does not equal 10 and x does not equal 8. Here's a second problem, and this one is for you to try. So pause the video, give this your best effort, and then start the video again when you are ready to check your work. All right, give it a try. Let's take a look here. So, domain of G. Well, this is nice. G actually takes any real number. How about the domain of F? Well, I need that whatever's underneath the radical sign, that has to be greater than or equal to 0. So x minus 4 is greater than or equal to 0. Oh, so add 4 to both sides. That means that x is greater than or equal to 4. In the previous example, I found the x that made my g of x not work. Let's actually take the opposite point of view this time. Which x make, we want g of x to actually work, to be good. Which x make g of x greater than or equal to 4? So then this will tell me the domain of the actual composition of the functions. So g of x needs to be greater than or equal to 4, so that, in other words, x squared minus 5 is greater than or equal to 4. I can subtract 4 from both sides. X squared minus 9 greater than or equal to 0. This is a quadratic inequality. I can factor the left, x plus 3, x minus 3, greater than or equal to 0. Solve the equality. We can see that it equals 0 at negative 3 and positive 3. The left-hand side is a quadratic in standard form, so it's a parabola that opens upward. So where is this parabola greater than or equal to 0? That's to the left of negative 3 and to the right of positive 3. So x is less than or equal to negative 3, or x is greater than or equal to 3. And that then becomes the answer to the question. That's the domain of f of g. Whenever these x's are put into my g function, then it gives me appropriate values that can be put into the f function. All right, our last idea is decomposing functions. Sometimes you start with a composition and you want to figure out what were the original f and g. So here's an example. Suppose f of g of x is the square root of x cubed plus 9. So what were the f and g? So f is the outside function, and g is the inside function. So f gives us the overall shape of it. So a good choice might be f of x equals the square root of x, because overall this looks like a square root. And then what's on the inside? G of x as the inside function could be x cubed plus 9. That works. The thing with decomposing functions is that decompositions are not unique. There's another solution. I could also say maybe f of x equals the square root of x plus 9. If that was the case, if that's the outside function, then what is the inside function now? Well, then it becomes x cubed. You see how that works? So you can have more than one solution when you are decomposing. Here's one for you to try. Pause the video and then start again when you are ready to check your work. All right, let's take a look. So for an outside function, we might say overall this has the shape of 1 over something. So simply 1 over x. And then inside of that, what is actually taking the place of the x? That would be the square root of x plus 4. Maybe you came up with a different solution. Another way to do this might be f of x equals 1 over x plus 4. Maybe you did this, in which case your g of x would be simply the square root of x. All right then, and with that, that finishes our material on composite functions.